Hello students, how are you all? I hope you are all doing well. So our today's topic is Wheatstone Bridge. Okay. And this Wheatstone Bridge is actually based on the application of Kirchhoff's rules. As we all know that Kirchhoff's rules there are two Kirchhoff's rules. First one is Kirchhoff's voltage rule, and second rule is Kirchhoff's current rule. Okay, so these two rules we are going to use here. So Wheatstone bridge is a, we can say, type of setup in which it is used, basically used to determine the resistance of a unknown resistor. Okay, so here as you can see in the setup, there are four resistors used: R1, R2, R3, and R4, where R1 and R2 resistors are already known resistors. They are called as known resistors. And I mean, their values will be known, R1 and R2. Let's say like R1 is 50 ohm and R2 is 100 ohm. Here, R3 will be the standard resistor, or we can say the resistor which we can change as per our requirement, or we can say to determine the value of R4, we will be varying the value of R3. And here R4 is the unknown resistor. Okay, so let me write here. This resistor we are going to find out. Okay, so the value of R4 we are going to find out. And here the one more thing here. Here one battery is applied, and its voltage is E, and one galvanometer is also applied here. Okay, one galvanometer is used here in the arm BD. Okay, you can see in the arm BD one galvanometer is used here. And basically, as we know that galvanometer is used to determine the current and the direction of the current. Okay, so for the spatial purpose, we use its balanced condition. Okay, and uh, first of all, let's see that, for example, let me mark the current here. For example, current I is flowing, total net current is current I. Okay, and here the current I1 is going through the resistor R1, and current R2 is going through the resistor R2, and current I4 is going through the resistor R4, and current I3 is going through the resistor R3. Now, for the spatial purpose, we use the balance condition. Okay, let me write. So it is balanced its balanced condition. Balanced condition will be when there will be no current through the galvanometer arm. Like in that case, in case of balanced condition, there will not be any current in the galvanometer arm. And one more thing, there are some assumptions like we have to mention here, that we are assuming here that there is no internal resistance of applied battery, because in general sense we can say that there is always some internal resistance, but here, to get the, we can say, convenient uh, derivation, or we can say taking the ideal condition, what we are assuming here, that there is no internal resistance of the external voltage that we are applying here. And for balanced condition, as we have assumed here, that it is the current in the galvanometer arm is, it is 0. So now we can apply Kirchhoff's current rule. Okay, or we can say Kirchhoff's junction rule. Okay, so first of all, let me apply. Now, first of all, apply Kirchhoff's junction Kirchhoff's junction rule we are going to apply here. So first of all, we will apply the junction rule at junction B. At this junction B, we are going to apply the junction rule. Okay. So as per the junction rule, we know that the the current which are entering in the junction and the current which are leaving from the junction will be equal. So here there are only three arms here, like the vertical and these tilted arms. So here we can see that the current I2 is coming to the junction and current I4 is leaving from the junction. But as per the balanced condition, there is no current through the galvanometer arm. So we can write here at the junction B. Let me write here first of all, at junction B, we can write here I2 equals to I4. I2 equals to I4 at junction B. Now at junction D, we should also write at junction D, we can see that the current I1 is coming to the junction and current I3 is leaving from the junction. And there is no, because we know that there is no current in the galvanometer arm, so there will be only two currents, I1 and I3. And since I1 is coming to the junction and I3 is going from the junction, so they will be equal. So at at junction D, at junction D, what we can write? I1 equals to I3. So I1 equals to I3, we can write here. Now we will apply Kirchhoff's voltage rule, or we can say Kirchhoff's loop rule. Okay. And the loop we are going to decide. Now apply Kirchhoff's loop rule. Sometimes it is written as KVL also. KVL means Kirchhoff's voltage loop. Kirchhoff's voltage law. Sometimes it is written as. Okay. Now the loop we are going to decide. So first of all, I am taking the loop ABDA. Okay. The loop ABDA. This loop I am going to take. So first of all, let me write loop. And when I'm writing here loop ABDA, it has some purpose, because we know that loop should be closed loop. So that's why I'm taking ABDA. Sometimes what we like, we do some mistakes also. So those mistakes should be uh, uh, those mistakes should not be committed. Okay. So here, so loop should be ABDA. That means we are starting from point A and we should end, we can say we can stop also at the point A, same point, then only it will be closed to. Sometimes the students what they do is they write the loop only ABD. That is not right. Okay, because what they think is that like all the points we have taken, so why to take the A again? We have to take the A again, because we are here. What we are taking the closed loop. Okay, so that's why we have to write ABDA. Okay, so now we are applying Kirchhoff's voltage law. So that's why in if I am starting from AB, then I have to write, because the current is also moving in the same direction as per the loop, so it will be I2R2. Let me write. So the equation will become as, it will become as I2R2. Then the first arm is completed AB. Now we are going in BD. As we know that there is no current in this arm, so we have to write 0 plus 0. Then AB is completed, BD is completed. Now D to A. Now we are moving from D to A. Our motion is from D to A, but the current is in the opposite direction. So we have to take the negative sign. So it will be minus I1 R1 minus I1 R1 equals to 0. Okay, so this will be the first equation, or we can write here I2 R2 equals to I1 R1, or what we can write here, we can write here that R2 upon R1 will be equal, because R2 and this R1 will be going in the denominator, so it will be I1 upon I2. Equation number 1. Now we are going to apply the Kirchhoff's loop rule in the another loop which is remaining. So second loop is the left one, this one. The loop is the loop I am going to take is, it is B C D B. The loop I am taking is B C D B. Okay, so loop is B C D B. So first of all, we will cover the BC arm and then CD arm and then DB arm. So in BC arm, we can see that in BC arm, there is unknown resistor and the current is moving, the current moving is I4. So we have to write I4 R4. The voltage will be I4 R4. So I4 R4, then BC is completed. Now CD, in CD we can say we are moving from point C to D, but the current is moving from point D to C. So we have to take the negative sign here. So it will be minus I3 R3, minus I3 R3. And now we are moving in the arm D to B. But as we have taken the balanced condition, so what we the current in the galvanometer will be 0. So my plus 0, whatever you can take, minus or plus 0, because we don't know the direction, because if it is 0, so it will be 0. So now the equation will be I4 R4 equals to I3 R3. This is the equation. Now as we can see here, I2 is equals to I4 and I1 is equals to I3. So we'll put this then in equation. Now let me mention here, this I4 is nothing but it is I2, and I3 is nothing but it is I1. You can see again, I1 is I3 and I2 is I4. So the equation will become as, it will become I2 R4 equals to I1 R3. Okay. Now we have to take the uh, we have to like the separate the resistance and current. So what we can take, it will be R4 divided by R3 will be I1 by I2. This is the equation number 2. Now equate the equation number 1 and 2, because we know that both the ratio R2 upon R1 and R4 upon R3, they are both equal to the same ratio of the currents I1 upon I2, and similarly in the second equation also I1 upon I2. So if we equate equation number 1 and equation number 2, what we will get? We write from equations 1 and 2. What we are getting from equations 1 and 2? We are getting R2 upon R1 is equals to R4 upon R3. Okay, so we should write here R4 upon R3 is equals to R2 upon R1. Am I right? Yeah. Okay. So R4 upon R3 equals to R2 upon R1. Okay, this is the, we can say, final result that we wanted to derive here. And this condition is called as balanced condition, or at this condition there will be no deflection in galvanometer, so sometimes it is called as null deflection condition also, so that is also fine. So here R4, R3, R2 and R1, they are all the values of resistances of resistors R1, R2, R3 and R4. Okay, so it is also, again we can write here that it is balanced bridge condition in terms of resistances. Okay, and this is called as null deflection also. So let me write that null deflection. Null deflection because we know that there will the galvanometer is basically used for the purpose of deflection. Galvanometer in respect, we can say in perspective of galvanometer, we are writing here null deflection. Basically, if we see that from where we started, the known resistors R1 and R2, and we have taken here one standard resistor R3 that we can change as per the as per we until or unless we are getting the null deflection condition, or we can say zero current in the galvanometer arm. Because if we start varying the value of R3, like we placed the R4 here, we placed the R4 resistor in the BC arm, and then our task is to take the value of R3 such that the galvanometer arm will not get any current. There will be zero current. So that condition will be called as null deflection condition, or we can say null deflection point in the galvanometer. And at that time, the bridge will be balanced. Okay. And the application of Wheatstone bridge is very important. If we study the meter bridge in our laboratory also, when we demonstrate the meter bridge experiment, in that we use the Wheatstone bridge. The application of Wheatstone bridge is used there. Okay, so there we take some unknown resistor R4, or let's say the name can be anything. So we take some unknown resistor, like we don't know the value of it, like it is for 500 ohm of 1000 ohm. We take the unknown resistor and we put that in the unknown arm, and then we vary the value of R3, and at the when the galvanometer shows the zero deflection, like the needle will be in the vertical position, then what we can see, that time there will be condition of null deflection, and we can find out the value of unknown resistor. So for that, the equation will become as, from this equation only we can find out what we can write here. It will be R4 equals to this R3 will be going in the right side, R3 times R2 upon R1. So this will be the, we can say, unknown resistor, the value of unknown resistor. Let me write here the expression. The expression or unknown resistor. So because we know that we have taken R4 as unknown resistor, so From there, we can find out the value of unknown resistor that is completely based on R, the value of R3, R2, and R1. So that's how the Wheatstone bridges work. And we will be able to find out the value of unknown resistor. And there are huge applications of Wheatstone bridge. Like we have some couple of experiments in our laboratory also that is based on Wheatstone bridge. Okay, I hope you understood this topic. And if you have any doubt, then you can ask in the comment section. I'll be happy to answer in the or like in the next video or in the comment section itself. Okay, thank you.